Hi folks, I'm going to take a look at number 3 from the Unit 6 assignment. So here they're asking us to find the zeros of these two functions. Now previously in the assignment they asked you to find the domains. Okay, so I'm just going to recall the domains because if I take a look, say at function 1, I see that it's a product of two functions that I know very well. And so in order to get an x-intercept for this function here, I have to see what might make the first function 0, and then that will make the whole thing equal to 0, or what makes the second function 0, which again would make the whole thing equal to 0. But just because one x might make the first function equal to 0 doesn't mean that it's in the domain of the second function. Okay, so that x makes this one 0 but is not valid for the second function means we'd have to eliminate. So not a bad idea to recall, and I won't redo it, but we found here that the domain of this function was all values from 2 to 10, including 10 but not 2. And here, the domain, well, the only restrictions on the domain were what made the denominator equal to 0, and the only restriction was that it couldn't be equal to 2. Okay, so it was all x in R such that x was not equal to 2. All right, so we'll keep that in mind as we're doing it. So let's start with A here. So what did we say? We said that it's a product of two functions, meaning it'll be equal to 0 when one or the other is equal to 0. So let's solve 10 minus x equals 0. All right, so that's our first option. Now here I could solve it by squaring both sides, but I think it's pretty clear that x is going to have to be equal to 10 in order to make this equal to 0. So there's one x-intercept as long as it's in the domain. And we see here that it is indeed in the domain. All right. So next we'll go to the second function. So the other option is that log base 3 of x minus 2 is equal to 0. Okay. And again, instead of solving this equation using algebra, I certainly could by rewriting this as 3 to the 0 equals x minus 2. I can also just remember that in order for a logarithm to be equal to 0, the input has to be equal to 1. So I know that x minus 2 has to be equal to 1, and therefore x is going to be equal to 3. All right. Now, is this in the domain of the function? And yes, it is, because it's within the interval 2 to 10. Okay, so just recall, I could have done this by also saying, that converting this exponential form, 3 to the 0 is equal to x minus 2. And lo and behold, it's exactly what I have here. Okay, x minus 2 equals 1. So there we go. Our x-intercepts then are 3 and 10. And again, we kept both of them because they were both in the domain of the function. Now we go to part B. Part B is a division. So we know that a quotient is equal to 0 if the numerator is equal to 0. So essentially, I just have to solve sine of x equal to 0. And of course, sine of x is equal to 0. Okay, just in case you don't remember, draw yourself a little graph. So here at 0, at pi, at 2 pi, etc., negative pi. So we remember that it's equal to 0 at all multiples of pi. Okay, so our x-intercepts, okay, are going to be all multiples of pi. Okay, we just need to make sure that none of those are in the restriction. The only restriction on this domain is that x can't be equal to 2, and 2 is not a multiple of pi. So that, again, is not affected by the restriction on the domain. So here we can say it's just equal to n pi, where n can be any integer. All right, and not surprisingly, we have infinitely many x-intercepts. All right. So just to recap, when you have a combination of functions, especially if it's an arithmetic combination, the first is to remember what scenario will give you an x-intercept. When it's multiplication, either one function or the other has to be equal to 0. And if it's a quotient, the numerator has to be equal to 0. So once you determine what you have to solve, you just have to make sure that what you get as an answer does not contravene the domain of the function. Anything that's not in the domain of the function, we would have had to eliminate. In this case here, there were none. All right, that's it for this one.